guess I have a license.
Hi everyone. Thank you for getting to 107 Elementary Astronomy with me. I hope you enjoyed it. This last class I want to do prep for the final. It's very similar to the midterm, except for this part. 0 points for no answers, half points for wrong answer, and then full points for correct answer. Basically answer the multiple choice, right? Because there's no recovery points for that level we did in the midterm, because I simply don't have enough time to do a whole hand it back to you, get your corrections, and then fix it. Okay, so we're going to do a bunch of multiple choice questions, get your voting cards out. We're going to be here on April 29th from 2:30 to 5 p.m. I fully suspect that I am the only person who's going to be here at 5 p.m. and most people do not need the full time, but I'm also not keeping time. I'm not going to be standing over you going, "You have 5 minutes left." I hated that as a student, so I'm not going to do that to you. Take your time to actually answer it. Make sure that you have your note card with you. I will bring the equations. You bring down, like, if you want to remember something, make sure that you put it on your note card. We'll have a couple of homework and group work questions, so something where you have to show your work. So very important to write down units, very important to write down how you got there. The rest is multiple choice questions, and then with 1 or 2 bonus questions, depending on how many you pick up. All right, so how big a note card? I didn't say that because everybody's handwriting is different. So again, I didn't say that. Try not to bother your neighbor, and I'm trying to have everybody sit about a seat away from each other so that we're calmly. So how to do the test, write everything down that you do know. So if you go like, I think it's this equation, I think we use it like this. And then please use the same notation as in class. It's like, what is this X time and that one here, distance? I actually had this conversation with somebody. And it's like, please tell me what things are, and stick to the convention in that case. And then use the unit. So if it has a unit, between the square brackets, this is the unit. If it's one of those weird astronomy ones, use that unit if you do the calculation, see what that, check that out. You bring the expressions, I'll bring the expressions, and I'll provide any constants as well. So the cheap line steel, please use this opportunity to, anything that you're not quite certain about, anything that you go, I'm not so sure if I'm going to be able to remember that, put it on your note card, right? This is the part where you summarize in conjunction with your brain what you think you're going to need and what you got away from this class, and steal from that all the time, steal from the slides, and steal from that note card. And that line card, always write down at least the bit that you do know, or the feeling that's like, it's this. Go to the back of the final, look for the equation that it's like, I think he means this equation. If you just copy that equation, you're already getting some points for this answer. If it's completely arctic blank, I can't give it any points at all. Right? I grade up. I'm not sure if I said that clearly enough throughout the semester, but I grade up. So basically anything you do, the points will accumulate, right? You can only go one direction. If I make a mistake and you take that out, your points can only go in one direction. You can only go up. And so I will calculate the how much of the in-class, pre-class, and homework assignments you've done. If you did 70% of them, you get the full 30 points for each. If you did not do the full 70% of them, I will, grade accordingly. So commensurately, what is the term? So if you only did 50% of them, then I'll give you like 15 points for that. Like you don't. It's always worth putting the last homework or something like that in. I'll go over the various topics and then just do the multiple choice questions. But is it clear how the final grade gets calculated? It's like trying to get more than one nod out of the room. Thank you, fantastic. Okay, so we're all feeling pretty calm about the final? Okay, take a shrug. Fine. And so we're going to go do some multiple choice today, and that's it. I'll see you on April 30th after that. Okay, so at the start, which star cluster is the oldest? So remember that all the stars start on the main sequence, and as they age, they move off the main sequence. And so as a cluster, you have NGC 2362 over here, and 67, you're over here, the purple line, M3. Here's M3, the red line, and the Pleiades, which is over here. So which one of these clusters is the oldest? Voting 1, voting 2, voting 3. The majority C, M3 is this guy, and he has the, he or she, I don't know, gendered cluster stars for no reason. And it stops all the way down there. So the further down the main sequence are, the older you are. You all got that. Fantastic. All right. Which star cluster is the youngest of all of these? 1, 2, 3. 3A, yes, they're all the way up here. And you see 3362. Which star clusters have red giants in them? So 2362, coma, here's coma, here's M3, and there's the Pleiades. Which one has red giants in them? 1, 2, 3. Yep, M3 all the way up here, red on this side. You're using the slides that I just uploaded to sneak a preview, like we're trying to figure out what that's good and not, right? Which one has brown dwarfs in them? 1, 2, 3. All of them, right? There's the little pretty things down there. Which star cluster looks the reddest? Is it this one, Pleiades over here, and 3 over here, or Coma? Where is Coma? There's 1, 2, 3. Yep, and 3 has that row of red giants. So I have a couple of different ways to basically ask the same question. You've got red giants in the cluster that's going to look a lot redder. But it all comes down how far down the main sequence MI is the turnoff, because that tells us how old the population is, how old the group is. Okay, black holes. So stellar black holes are formed by a lack of any light in the region of space, supernova from the most massive stars, supernova from binary stars, or collapsed dark nebulae. How do we get a black hole? 1, 2, 3. Short B. Big supernova. What is the density of a black hole? Less than that of a neutron star, about the same as a neutron star. Infinite. A co-count. 1, 2, 3. It has no size, so it is an infinite density thing. So which of the following lists the correct order as a possible evolutionary path for a star? You start with a red giant, go a neutron star, then a white dwarf, then nothing. A red giant, supernova, planetary nebula, neutron star. A red giant, planetary nebula, white dwarf. A red giant, planetary nebula, black hole. What is the one that works? I've got every answer here. So you start with a red giant, and you can then shed everything and become a white dwarf. If you are so if you become a red giant, you essentially lose everything, diffuses out, and you end up with a little white dwarf left. If you have a higher mass star, you're going to basically go supergiant, explode for sure, and either become a neutron star or a black hole. So if I end up with a white dwarf, I go through a red giant phase like the sun, these mass stars, they end up as a white dwarf. If I'm higher mass, I for sure explode, and then I end up as a neutron star or a black hole. All right, I didn't talk as much about telescopes as I'd like, so I can sort of skip this part, but the main thing to take out of that is that the resolution comes with the diameter of the telescope. So if you have a certain wavelength and a certain diameter of a telescope, that gives you a sort of number. That ratio is a number for the resolution. And the smaller it is, the better you can tell little blobs apart. So I think we did cover that part, which is the most essential part about telescopes, because people tend to have a tendency to buy the biggest possible tube they need, and often it's not necessary. But we do get that wavelength, and like going to a different wavelength means that you have to have a different diameter telescope to get the same resolution. So I'll skip this part because we didn't do this as much. And I'll not have this question, or I can explain that. Sorry, I'll explain it briefly because I really wanted to, but it was sort of just as an illustration. So if you observe at one wavelength and at a diameter of 2, you have a different one that observes at 10 centimeter and at 300. Which one of those two telescopes has the lowest number of R? And that ends up being the ultraviolet telescope. But it depends on, so even if you, despite the fact that you have a 300 meter class, like basically Arecibo, because it observes at 10 centimeter, the ratio is, means that the R value, the value of R is higher, so it is a low resolution telescope. So I'm going to skip this part, but it basically comes down to location. We didn't talk about this as much, but it comes down to there are a couple of windows in our atmosphere that are easy to see through. So where do you put an optical telescope? Somewhere nice and dark, so you can see where all the people live with all their lights. And so where you put a radio telescope, again away from people, and where you put an ultraviolet telescope, you don't put it on Earth, right? So you edit those slides. Essentially, I'm not going to ask that question because we did spend a class on telescopes. We just did it like 5 minutes. So if you come across something about telescopes, it'll be simpler. Okay. What's an exoplanet? A planet in the outer edges of our solar system, a planet expelled from its parent system, any planet discovered outside our solar system, a planet that people thought would exist in our solar system. What's an exoplanet? Voting in 1, 2, 3. Everybody remembers that. Great. What is a hot Jupiter? A cocktail, a phase Jupiter goes through, a Jupiter mass exoplanet close to its parent star, a whole section of Roman mythology. Voting in 1, 2, 3. Okay. Around what type of star were the very first exoplanets discovered? Can you remember that? A sun-like star, a brown dwarf, a red giant, or a pulsar? 1, 2, 3. I've got a mix of answers here. The very first ones were around pulsar, but again, that's sort of like a factoid, so I would be jumping there to ask those. Can a place like Star Wars Tatooine be real? What is your opinion on that? Voting 1, 2, 3. I have one person who's not a fan of Star Wars, and everybody else thinks like, yes, this is going to be fine. Actually, we just found another one. So this is a planet that actually goes in a polar orbit around two stars. So that sounds like an absolute bananas planet here. So yes, we can have Tatooine, and we have actually nicknamed a few of these. So there are 5 ways that we can find exoplanets, right? We can find it with direct imaging. We make the biggest, best telescope, and we actually resolve these things out. We do the transit method, so these are eclipses, radial velocities, astrometry, and microlensing. These are the 5 ways that we can find exoplanets around other stars. And so if this planet, you see this little dotted line here, so I'm realizing it's completely washed out. Can you see it in the room? Okay, great. So you can see the orbit, and we're looking sideways onto this star, this planet. Can I see this with direct imaging, transit method, radial velocities, astrometry, all of the above? Which one was it? 1, 2, fold it all the way out. Okay.
On what planet, or like what planets could not be detected the other ways? Like, I understand if it's transit method, we might not be seeing it like head on, but like, what about the other?
Right. Direct imaging has to be separated out enough, and the star has to be close enough. So can I actually resolve it with my telescope? It's a bit of a moving target. Our telescopes get better, move out a little bit. Transit method, again, you have to be in the plane of the motion. If it's like this, I don't see it in the transit. I don't see it in the Doppler shift. In the astrometry, it's the other way around. It has to actually move up and down a bit. I don't want transverse like motion towards me, away from me. So these two are sort of complementary. If I see the planetary system on its edge, I can see it very well with radial velocity, but I can't see it with astrometry as well. It might jiggle a little bit. But if I see it checking what date we've all collectively forgotten, or I didn't cover well, or what would happen. So if I'm looking directly from the top and it's right close to the star, can I see it with direct imaging, transit method, radial velocities, or spectrometry, or all of the above? Which one can I see it best with? I'm looking off the top, so I'm looking top down, and it's orbiting like this. Which one can I use here? So I use 1, 2, 3. See some paint faces, that's not good. So if it's really close, direct imaging gets really, really tricky. So transit method, nope, it's not passing in front of the star. As radial velocity, it is moving the star and the planet are moving in the plane of the sky. I'm looking on top of it, so it's not moving towards me or away from me, so that's out of 2. And so only astrometry is the one that I can find. So I find these different techniques sort of really illustrate for us that if you are doing science, especially if you're doing observational science, that every technique that you're using is going to only see some of the truth, right? It's almost like the Indian myth with the 4 blind men that all get introduced to an elephant, and they go like, it has a tail, it's got like a really rough skin, I feel like a leathery wing, right? You get 4 different perspectives because they're all talking about a different component. And so piecing it all together is really a big part of this science there. And so how can this planet be detected if it's like nice and far out, direct imaging, transit method, radial velocity, or all of the above? Well, it's far out, so what do we want? 2, 3. Nicely separated, you can direct image that. Yes.
Sorry, back to the last one. I'm just confused. Why? Like, what's the difference between astrometry and radial velocity? Like, what's radial velocity? Because I thought it was like if you're looking at it from the top view.
Radial velocity sideways, along the radius, along the.
Okay.
Okay. No, this is fine. That's exactly what I wanted. So I'll find the slides for that in a second. I say that very confidently, but I always get flustered. So this is we did direct imaging, we did transits. Radial velocities, if I go to Earth, right, if I'm looking at it sideways, this is, maybe this, video work? Yes. So here we're looking almost sideways on it, and that means that the planet sort of, in the thing in the back of my head is literally the 2 ice skaters that are holding hands and that are like rotating around this common center of gravity. That is what's happening here. Talk too long, no problem. So then you see the stars sort of rock towards you and away from you, and that's the radial velocity, right? That's the thing that you see, like I'm seeing the star move toward me. It's blue shifted a little bit, and it's moving away from me, it's red shifted a little bit. That's the radial velocity part, and so that's the one that you see here, where you see the lines shift back and forth. The tricky part was actually measuring a shift that small. But once you can, you actually pick them up. But astrometry, we're looking at it top down. So now we're looking from your perspective on the top, like we're looking on one of the poles. And so that's where you see the star move back and forth with respect to relative, like nearby stuff. Right? You see we're looking top down and it's moving around. So astrometry sort of catches the ones that we didn't get from radial velocity.
Okay.
Because it's moving in the plane of the sky, it's not moving towards us. Okay. All right, one of these things tells us, or which one of these tells us the orbital period. Which one can we measure how long a year is on this planet? Can we do this from direct imaging, the transit method, radial velocities, or astrometry, or all of the above? Where do I get the year from by doing this, right? So 1, 2, 3. Majority B, so you think transit method definitely gets you the period. Radial velocity also repeats. Astrometry also repeats. And the direct imaging, I can look at you half a month later and still see how much you've moved, right? So all of them can get us the period. It takes different amounts of work. Transit and radial velocities are so these three in the middle gets us the period quickest, but you can get the period every time. Now, which one of these gets us the radius of the actual planet? The transit method, radial velocities, astrometry, all of the above. So 1, 2, 3. I got B a lot, and I got a small, and I got about half B, half A. Majority B. Okay. Transit method is this one, right? Where it passes in front of the parent star. So we see how much it dips. So we see how much is covered by the planet. If we know how big the star is, we know how big the planet is because it covers a certain percentage of it. So transit method is the only one that gives us the radius of the planet, the actual size of this thing, the disk. How big is that disk? Everything else, this gives us a mass, that gives us a mass, but it doesn't give us how big the disk is. This is why transits were so neat to find. Remember that we have Kepler's 3 laws, so all planetary orbits are ellipses. In an orbit, the planet sweeps out an equal amount, right? So it goes through this in an equal amount of time as it goes to this part of the orbit. Everybody remember that part? See one person enthusiastically nodding, and now my brain is translating that to everybody knows it was this one guy's nodding really hard for all of you. That's not how it works, does it? All right, and so the last part is the period and the major axis relate as the period squared is the major axis cubed. So these things still hold true. So if I can get the average distance from the planet and the star, for this particular, like it's going underneath, it's not going in front of the parent star. Direct imaging, transit method, radial velocities, astrometry are all of the above. Which of them can tell me the exact distance between the star and the planet? One, two, I realize I made a mistake. This one, transit method would work, right? So we couldn't get the period, so we can't get the average distance from Kepler's laws. So with this one, I can only do this with radial velocities, since it's walking back and forth. I get the period that way. But this is not a good question because I could maybe do this. It's ambiguous. Just realizing that. But if you see an ambiguous question, I think I did this every year. I was like, oh, that's an ambiguous question. So if you see a question, you go like, I don't think this is I can answer this clearly. Let me know. Because I often have something like this in there. I don't say often, but I've had it once or twice, and so I want you to speak up because A, you'll get extra points. I can only make a mistake in everyone's favor. Okay? If I make a mistake, ask. That's it. If you go like, no, there's a single answer here, that's fine. No extra points. You go like, oh yeah, you can interpret that question that way. I proofread it 3 times. There's always a typo that manages to get through. If I get a question wrong or ambiguous, please let me know. Okay, what does the habitable zone depend on? The distance between us and the star, the type of the host star, the size of the planet, or whether the planet has an atmosphere. One. A, B, and D. The distance between us and the star, how far that star is that important for how life is on that planet? Yeah. Right. It doesn't matter how far we are from that planet. It's important how far that planet is from its parent star. The type of the host star, if it's a big difference if we're around an O star, if our planet is around an O star or an M dwarf, right? If really depends on how hot it is on the surface, depending on the host star. Is the size of the planet important? No, because we're just asking if it is in the habitable zone or not. Right? You can put Jupiter in the habitable zone. You can put Saturn with its moon Titan in the habitable zone. And whether or not the planet has an atmosphere, we don't even know that yet. So the habitable zone is exclusively what type of star it is, and then how far away from that star you are. The habitable zone for the Sun is somewhere between basically Venus and Mars are sort of in the habitable zone, and then also, of course, in the middle. But if you are looking at really small stars, the habitable zone creeps closer because it's not a big campfire, right? Think of the campfire analogy, right? Is it a big fire like the Sun? Well, then it's all the way out. But if it's like Lisa 581, which is a tiny N, or maybe like K-worm, then you're much closer to that. You need to be much closer to be warm enough to have it. Notice that the edges are a bit fuzzy because, well, it depends a little bit on your stellar model, etc. Right? So whether or not you're trying to walk. All right. Which planet detection method is repeatable? The transit method, the radial velocity method, direct imaging, or all of the above? Which one of those can I do again with a different telescope is repeatable? 1, 2, 3. Excellent. They are all repeatable, which is why they're so they are good for scientific verification. Which is why you get lensing. That is why everybody skips lensing, because like you see it and then you sort of did I? Okay. We had the Drake equation, which some of my colleagues don't consider the Drake equation real science, but I think it's an incredibly useful thing to do where you go, well, I have some of these numbers estimated and I can argue others. And so you have the rate of stars being made in our galaxy. That we know pretty well. The fraction of those that have planets, the number of those planets, so the number of suitable planets for the planetary system, so the ones in the habitable zone, fraction of those that will have life on it, fraction of those that will have intelligent life on it, fraction of those that will have civilization on it, radios, and then the length that takes, and so that gives us a total number in our Milky Way of civilizations to talk to at any given time, who are, online. So which one of these, the number of stars being produced, the fraction of those with planets, the number of planets in the habitable zone, or the length of the civilization, which one do we have no constraint on at all? We have no idea what that number is. So 1, 2, 3. Yeah, we don't know how long civilization lasts. We're still in our first one, basically. So we don't know how long they'll be talking over the radio, but we do know how many stars are being made. We have a good estimate of that from the Milky Way. How many of those have planets, and how many of those planets are in the atmosphere. All right, so if I look at an atmosphere, for example, ours, so which one of these molecules, so we have methane, nitrous oxide, oxygen and ozone, carbon dioxide, and water, which of the molecules are added to the atmosphere by combustion? If I burn hydrocarbons, which ones are added? A, nitrous oxide, B, oxygen and ozone, C, water, or D, A and C combined. Going 1, 2, 3, you all got it already. You also have the water comment, right? So which molecule protects us from ultraviolet radiation? Voting 1, 2, 3. Unanimously C. Fantastic. Yes, it's the ozone layer. And so which one of them are removed from the atmosphere by combustion? 1, 2, 3. Oxygen, right? Because combustion is literally combined with oxygen. You can argue like methane. Which molecule should I avoid if I want to observe at 1 micron? So look, 1 micron is here. Which molecule should I not want to be around? 1, 2, 3. So which set of planets forms a class? Earth, Venus, Jupiter, Pluto, Earth, Mars, Jupiter, and Saturn, Mercury, Venus, Earth, and Mars, Jupiter, Saturn, Uranus, and Pluto. Which one of them is a class on there? Which grouping is a class? Right? 1, 2, category 3. Yes. Mercury, Venus, Earth, and Mars, the rocky planets. New one, which set of planets forms a class? Earth, Venus, Jupiter, Pluto, Earth, Mars, Jupiter, and Saturn, Mercury, Uranus, Earth, and Mars, Jupiter, Saturn, Uranus, and Neptune. Oh, you got it. All right. It takes you guys less time to vote than you can read it out. Okay. Okay, what is Pluto? A rocky planet, a gas giant, a port cloud object, or an icy dwarf planet? How do we classify that? One, two, three. Who's still angry about the fact that Pluto is no longer officially a planet? It's always a remarkable large number of people. It's been 10 years already. Okay, so what causes aurora, the northern lights? The space gerbils, the gas combusting at high altitude, the thunderstorms at high altitude, or charged particles hitting the upper atmosphere. One, two, three, okay. What formed the rings of Saturn? You remember, the disintegrating moon is still a forming moon. The Mimas is really a Death Star. The leftovers from Saturn's formation. 1, 2, 3. A few more on D. That was the idea originally, but we now think that the moon is disintegrated. So it's one of those things that shifts. Or has shifted. What causes the gaps, though? The moons that sweep through, the resonances with the Saturn's moons that were just where the moon disintegrated, the ice evaporated at certain radii. Why do we have gaps there? 1, 2, every gap has a moon. So we get resonances. I'm not sure if I covered it. I've noticed that there's a bit of spreading answers here. So I did cover it with the resonance of the moons of Jupiter. I know that because I have a slide on it, right? The moons are the pattern is like a chord. It's like you have, this one goes around once, this one goes around, well, this one goes around twice, that one goes around once, and the other is like 2/3 of the smallest one. So they're on equal ratios of their orbits. And so that happens because if they're a little off that, they basically pull each other back into that orbit. So you can have that with the particles in the rings of Saturn as well. So they get resonated out of certain rings. And so that's what the moons of Saturn are doing. Okay. I'm going to ask that one. Okay, what are the ranking from most to least of these galaxies according to mass? So dark matter, stars, interstellar medium, planets, supermassive black hole, dark matter, interstellar matter, stars, planets, dark matter, interstellar matter, stars, supermassive black hole, planets, interstellar matter, dark matter, stars, supermassive black hole, planets. So rank them from most to least, right? 1, 2, 3. See here. So you picked it. Dark matter has to start with dark matter, and then interstellar matter, gas is next, and then that sort of hopefully got you into the right order. So more gas than there are stars, supermassive black holes, and planets are sort of the rounding error. Using equations, we can actually measure something as long as we see something orbit around it, right? So if we can tell how fast it's going and say, all right, it's going around in a circle, that gives us a radius. That tells us that if I have the velocity, I have the radius, I have a constant here, and I can say how much mass is enclosed. Basically, move that r over here, this r squared goes over here, I drop one of the r's. Velocity is the total enclosed mass times the gravitational constant divided by radius. So if I know that, I can then observe a group of galaxies on the edge of the group, 1 megaparsec from the center. A small galaxy orbits with a velocity of 500 say, okay, if I have to convert megaparsecs to kilometers, I need to know what that unit conversion is, right? So if that conversion is there, you can say 1 megaparsec is this, 10 to the really large number of kilometers, and turn it into meters. If I have the gravitational constant, it's also in meters per second, so it's also in the system international. And I've got the velocity in 500 kilometers per second, so I need to put 3 zeros behind it to get it in meters per second. Do you think you can calculate that? Okay, see how we get there? So that's something to try out. If I'm looking at a picture of a galaxy, right, and we look at these, and they have the blue stars here, the massive blue stars in the spirals. What kind of stars color this region so blue, right? And here, B, C, D. Yep, it's O stars. Thank you. It's those. A. There we go. What kind of stars make the color of this region? A, B, or C? It's yellow. So you can always go like this is yellow here in the middle. So it is mostly. If it's not A, it can be A because that's blue. C is too red. D is faint. So B it is. If I look at these, and this is all yellow. What kind of stars make the color of this galaxy here? One, two, three. Nice. All right, so if I now look at it in real good detail with Hubble, and I actually take a little picture here, and I've got a clump of these stars here, what kind of stars make the color of this region? What are those? 1, 2, 3, what are O stars? All right, I've got a single star here. What kind of star would that be? Is that B star, C star, D star, A star here? Sorry, A, B, C, D. 1, 2, 3. A. It's red and it's giant, so it's over there. It's region A here. We answered that. I think we had some confusion in class. So if you look at a galaxy that consists of mostly red stars, have blue stars, but they're not present anymore, right? They used to have young stars, so they're called young stars because they don't live that long. So if you see the O, B stars, the really blue, bright stars, they're going to be gone very, very quickly. But they were present at some point. It's just, everything has aged out. What violated the isotopic principle? The Earth is the center of the solar system, the Milky Way model where the sun is roughly in the middle. The point of view with the great debate that the nebulae were within the Milky Way, and that was all there is, are all of the above. 1, 2, and 3. Thank you. Yeah, it's all of them, right? All of them gave us a special place in the universe, and so this is also why we came up with the isotopic principle as a. If your theory requires us to be in a special perspective, special piece of time, special part of the universe, that's probably going to be needs further examination. Putting these constituents of the universe in the right order, right, from most to least, right? So dark energy, dark matter, gas and stars, dark matter, dark energy, gas and stars, dark energy, dark matter, stars, gas, dark energy, gas, dark matter, stars. Which one of them is the most? Start with dark energy, 73% of the universe is dark energy, then 23% is dark matter, and then the rest is a rounding error, but there is still more gas than stars in the universe. So this is a plot to remember dark energy, 73%, something is pushing out the universe, like that's the quality of the vacuum of space. That has a dark energy component. 23% is dark matter, which is a stuff that we only see gravitational effects of. we know about dark energy, supernova distances in the redshift, galaxy redshifts, the cosmic microwave background, measuring the vacuum on Earth, or A and C combined. One, two, thank you. Yes, it is both the supernova distances and the cosmic microwave background. The fact that both of them found that is how we now know for sure that there is something called dark energy. Okay, so this is one about that lambda over d. So it's a question about resolution. And so the cosmic microwave background observations got better every time. The cosmic microwave was always observed at 500 micrometer. So it is always the lambda is always the same. Rank the telescopes in diameter. So the further you get, the better you have to change the diameter of the telescope. Kobe, Planck, WMAP, Kobe, WMAP, Planck, Planck, WMAP, Kobe, WMAP, Kobe, Planck. Which one is the best order, like size-wise? Putting in 1, 2, 3, Kobe, WMAP, Planck. Yes, we get better resolution every time with a bigger telescope. All right, so the expansion of the universe, where we get like reincarnation, as close as static as you can be. It expands first out of that, or it's just expanded faster. It just speeds up. It's the fact that we now live at the point where the scenarios would start to differ, not a violation of the isotropic principle. Yes, no time or place is special. No, it's a principle, not a law. And I just want the specific end. Voting in 1, 2, and 3. That was my last question. I definitely see a couple of D's here in the audience. I get you. It is a principle, not a law. We're not sure that is going to be a problem, but it's something that is making everyone in the cosmological community a little uncomfortable because we didn't pan out the last 5 times that we thought we figured out the universe. So we'll see. Let's see. Do you know someone who thinks they're at the center of the universe? Is that a violation of the isotropic principle? Yes, no time or place is special. No. 1, 2, 3. Thank you. All right. Can you tell I was getting a little punchy? All right. So thank you all for sticking with me in this semester and doing astronomy with me. I enjoyed having you all here in class. And just to give everybody nice fuzzy feelings, here's again. Are there any other questions? Do you need me to help with anything? If you have any work you want to still hand in, I had somebody who was like, yes, I have a stack of paper. I will give it to you. I will take it. I will grade it. We'll see you all on here back in the planetarium for the final